Here we have the function 6 plus 2x squared minus x to the fourth, and this is what the graph looks like. And for this graph, we say that this blue part right here, we say that the graph concaves down, and then this piece, we say that the graph concaves up, and then this piece, we say that the graph concaves down. And so it looks like from the left side all the way up to about negative 0.5, that's where the blue part is, the graph concaves down. And then from negative 0.5 to positive 0.5, we say that the graph concaves up. And then from 0.5 to the right side, we say that the graph concaves down. So let's write that down. So from graph concaves down, that's the blue part, on the interval from negative infinity. It looks like it's about negative 0.5, but we don't know for sure. So we have to use the second derivative test to figure out what the exact value is. And then graph concaves up on the interval. It looks like negative 0.5 to 0.5. And then graph concaves down again on the interval from 0.5 from here all the way to the right side. So that's by looking at the graph. And then also it looks like we have a relative minimum maximum at the point negative 1, 7. And then also 1, 7. And then we also have a relative minimum at 0, 6. So that's just by looking at the graph. So we have the graph f of x as relative minimum at 0, 6. And f of x as relative maximum. It looks like it's about negative 1, 7 and 1, 7. And then again, this point right here, so from here to over here, that's where the graph concaves up. And then when we get to this point right here, the concavity changes. And so we have a point of inflection right here, and then we have a point of inflection right here. And to find these 2 points of inflection, we get the second derivative and set it equal to 0 and then solve for x. So all of this is just by looking at the graph. And now we'll use the first and the second derivative to make sure that we get the exact values right here. So the function. So now let's get the first and the second derivative. So the first derivative is 0, and then derivative for 2x squared would be 2 times derivative of x squared is 2x, and then minus derivative of x to the fourth is 4x to the third. So we get 4x minus 4x to the third. So this is minus 4x to the third. And then the second derivative is going to be 4. And then 4x derivative of 4x is just 4. And then derivative of 4x to the third is be 4 times. The derivative of x to the third is 3x to the second. So we end up with 4 minus 12x to the second. And then now we set the derivative, the second derivative equal to 0. And then we solve this equation right here for x. So subtract 4 from both sides. And then dividing by 12, negative 12. And this is equal to 1/3. And then take the square root of both sides. So we get x equal. And again, when we take the square root of the left side and the right side, we need put plus minus in the front, 1/3. And this square root of 1/3 is approximately 0.0577. And so that's what we saw right here. It looks like about negative 0.5 from the graph, but the actual answer is the square root of 1/3, which is about 0.577. And now we need to find the corresponding y. So let's write this way. So we have the square root of 1/3. And this comes out to be about 6.55555. And so that's what this point is the square root of 1/3 and negative square root of 1/3 and 6.555. And so this point's the same thing. Instead of negative square root of 1/3 is positive square root of 1/3. And so similarly, if we do negative, that'll be the same thing. So points of inflection are, we have the negative square root of 1/3, and this number and that. And so now we can talk about concavity. Well, now we can discuss concavity. So we started this function right here. The blue part would be from the left side up to the negative square root of 1/3. So graph right here. So concaves downward on the interval from negative infinity to the negative square root of 1/3. and then concaves up. And let's go ahead and put this also on the interval, that interval, and the interval from, and then the green part, that's going to be from the square root of 1/3 all the way to the right side, which is positive infinity. So it'll be the square root of 1/3. And then the graph concaves downward, upward on the interval. It's going to be from here to here, the red part. That's where the graph concaves up. So that's going to be from negative square root of 1/3 to the square root of 1/3. And so, and then also the second derivative test, if we pick any number inside of this interval right here, and then evaluate it with the second derivative, then we will end up with something negative. So this is the second derivative right here. And let's pick the number from this interval, the blue interval right here. So let's pick -1. So we do this, and so we're expecting something negative. We should get a negative answer for f at -1. And this comes out to be -16. -4 minus 12 is -8. -1 squared is 1, and then times 12, and so we get 4 minus 12, which is -8. And so if we have an interval where the graph concaves down, if we pick any number from that interval, and then evaluate, and then use the second derivative to evaluate at that number, then we'll get a negative answer, which is less than 0. And then let's pick one from the green interval, which is this one. And so let's pick 1. So let's put right here, test value x equal to -1. And now let's pick 1. So we'll pick 1 from this interval. Then we get f of 1. This is going to be the same thing. This will be -8, which is less than 0. And then now we pick something from the red interval. And then we should expect the second derivative to be positive. And so in here, in this interval here, let's pick 0. And so we pick 0. Then 0 times 12 is 0, and then 4 minus 0 will be 4. And this is greater than 0. So one more time, on the intervals where the graph concaves down, if we pick any number inside of that interval, then for the second derivative, we'll get a negative number, which means the second derivative will be less than 0. And then for interval on which the graph concaves up, then if we pick any number inside of this interval, and then the second derivative would be positive. And now let's also find the relative maximum and the relative minimum. And recall that to find the relative maximum, the relative minimum, we would set the first derivative equal to 0. So here's the first derivative. Because there's also a connection between the second derivative and the relative maximum and minimum. So here's our, so let's write that down. So to find maximum or minimum So we set this equal to 0 and solve for x. And so the common factors here would be 4x, and then we get 1 minus x squared, then equal to 0. And so here we have 4x equal to 0, or 1 minus x squared is equal to 0. So right here, dividing both sides by 4, we get x to be 0. And then over here, we get x squared equal to 1. So move the x squared to the right side, and then we get x squared equal to 1. And then take the square root of both sides. Then we get x to be plus or minus 1. And so critical numbers are, we have 0, -1, and 1. And then now to find the point where we have relative maximum, minimum, then we need to find the corresponding y value. So first let's do 0. So we have 0. So right here, when x is 0, and this is equal to 6, so when x is 0, y is 6. And then if we look on the graph right here, 0, 6, that's why we have a relative maximum. So that's where the function has a relative maximum. And then now let's do -1. And this will be 6 plus 2 minus 1, which is 7. And so we have -1, 7. And then we look on the graph, -1, 7, that's a relative maximum. This should be minimum. This should be minimum. Now we have maximum. And then similarly, if we have a 1 here, then we also get 7. And so here we have 1, 7, and this is a relative maximum also. And so summary, the function has a relative minimum at 0, 6, and relative maximum at -1, 7 and 1, 7. And now if we take the second derivative and evaluate it at the critical values, and then we'll also see this. So we want 0. So finding the use of the function and then evaluate the function at the critical numbers, that will help us find relative maximum, relative minimum. But here's what the second derivative will do. So this will be 0, and this is 4, which is greater than 0. And this is -1. And this will give us -8, which is less than 0. And then this is 1. And this is equal to negative 8, which is less than 0. And so the critical points where we have 0 right here, so if we evaluated the derivatives, the second derivative at 0, then we get something that's positive, and that tells us that we have a minimum. And then the second derivative at negative 1 is less than 0, so that tells us that we have a maximum at the point negative 1, 7. And then the second derivative at 1, so 1 is right here. And then the corresponding point is 0, 7. It's 1, 7. And the second derivative is negative, and so that tells us that we have a maximum. And so to find relative maximum and minimum, what we can do is use the first derivative and then find critical numbers and then evaluate the function at those critical numbers, and that will give us the relative maximum and minimum. The other way is we can also use the second derivative and then evaluate the second derivative at the critical numbers, 0, negative 1, 1. And if the second derivative, if it's positive, then we have a minimum. And so right here, it says that we have relative minimum at 0, 6. Because the second derivative is positive. And then right here, we have relative maximum at negative 1, 7. And then right here, we have relative maximum at 1, 7. So that's the connection between the second derivative and relative maximum and relative minimum. And so once again, to find relative maximum or relative minimum, we can use either the first derivative or we can use the second derivative to help us find relative maximum and minimum. And then the second derivative is also used to find points of inflection and intervals of concavity. Intervals where a graph concaves up or concaves down.